The second reaction of alcohols that we're going to look at is called oxidation. The oxidation reaction is a hard one for me to draw a generic version of it, like the way that I drew this generic reaction up here. I can't really do that for oxidation. I just have to go straight to some examples. So there are three different ways that oxidation can occur, three different types of alcohols that can be oxidized. I'm going to draw all three different types of alcohols because first thing that we're going to do is talk about how these different types are different. So leave yourself a little bit of room because we're going to need to fill some reactions in here. So there's three different types of alcohols. So let's start by focusing on how are these alcohols different from each other, what makes them unique. The first one, you can see the alcohol part of the molecule is at the end of its carbon chain. It's attached to a carbon, and that carbon that it's attached to has two hydrogens on it. The second type of alcohol that I drew, this is one that has the alcohol, the OH group, inside, in the middle of the chain. So it's not at the end of the carbon skeleton, it's somewhere in the middle. And this OH group is attached to a carbon that has one hydrogen attached to it, only one. So these two are different. The third type of alcohol that we have is an OH group that again is not at the end. It's not at the end of a carbon chain. It's somewhere in the middle. And this OH group is attached to a carbon that has no hydrogens attached. So these are three different types of alcohols. And they all respond a little bit differently to oxidation. So for oxidation, the reagents that we use, there's a variety of reagents that we use for oxidation, and rather than writing them all out, we just put a capital O in square brackets, and that is just used to represent any sort of oxidizing reagent or chemical, of which there are many. There's a lot of different possibilities. When we do an oxidation reaction, I'm going to erase this highlight on this. When we do an oxidation reaction on an alcohol, we remove the hydrogen from the OH, we take this hydrogen off, and we remove one of the hydrogens from the carbon that is next to the OH. So those two that I've highlighted in green, they get removed from the molecule. And so that's going to leave us with, we've got that one hydrogen left behind, and we have the oxygen left behind. And because we've removed those two hydrogen atoms, we need to create a double bond in between the carbon and oxygen to make sure that everything has the correct number of bonds. This molecule is a functional group called the aldehyde, which we haven't studied yet, but we will. So we're going to come back to the aldehyde in a second. Before that, we're going to move on to the next guy. And I'm going to delete the highlight off of this guy as well. So let's practice that again when we're oxidizing this alcohol. Remember, when we're oxidizing an alcohol, we're going to remove the hydrogen from the OH. And we're going to remove the hydrogen from the carbon that's attached. So both of those guys go away. And we're left with this. There's no hydrogens on this carbon anymore. It's gone. And we have to create a carbon-oxygen double bond This functional group is called a ketone. We need to create that double bond to make sure that all the atoms have the right number of bonds. So let's look at our last type of alcohol. And again, to oxidize, we need to remove the hydrogen from the oxygen, and we need to remove a hydrogen from the carbon that's attached. However, this carbon has no hydrogens on it. And because that carbon has no hydrogens on it, this type of alcohol cannot do this type of reaction. There's no reaction happening here because we don't have a hydrogen in that one particular location. So let's go back up. I said the aldehyde, we're not quite done with it. Let's go back up to the aldehyde. The aldehyde is special in that it can continue to react with the oxidizing agent or oxidizing reagent that we're using. If we have lots of extra oxidizing reagent present, then it will grab an oxygen from the oxidizing agent, and it will kind of magically just stick it in the molecule just like that. And this is called a carboxylic acid. So let's just practice a couple more examples of this reaction. Let's practice, what if we have this molecule right here, and it's, we're gonna react it with O. And what is the product of this reaction? So what we want to do, first of all, I'm going to find our OH group and highlight its hydrogen because we know that guy's going to go away. And now we need to focus on the carbon that's attached to the OH group and make sure that that carbon has at least one hydrogen on it, which it does. It has only one. And let's highlight that hydrogen because that hydrogen's going to go away as well. Redraw the molecule without the hydrogens that have been highlighted in green because they're gone, and make a carbon-oxygen double bond. So there's your product. Let's try one more. Let's do this guy right here. And let's say we're going to oxidize it. And I'm going to put this new word here, excess. You know what excess means. It means extra. So when we see the word excess in this reaction, that means that we have lots of the oxidizing agent, and the reaction will do 2 steps. Let's scroll back up, see what that means. 2 steps, like 2 steps all the way. We've got plenty of oxidizing agent. We're going to just do 1 step at a time though. So we're going to start by highlighting the hydrogen, and we're going to find the carbon that's holding the OH, and we're going to draw the hydrogens onto that carbon. Pick one of them to be removed in this reaction. Draw the product. You're leaving off anything that's highlighted in green, and you're creating a carbon-oxygen double bond. That's the first step. Second step, this is where it magically sticks an extra oxygen, always in the same spot, right there in this molecule. Just to be extra clear, with this particular reaction right here, even if you have excess, this one can only do one step. The only reaction that's able to do 2 steps is the first one that we looked at. And then, of course, this one down here, this does 0 steps because it doesn't have any hydrogens in the right spot.